All right. Well, welcome everyone. I'm Philip and this is Sanjoy. Today we're going to be talking about garbage collection in LLVM. Specifically, we're going to be talking about sort of how to support a sort of advanced collectors in LLVM without making a lot of changes to LLVM itself. I want to note this is not going to be a talk about how to make LLVM garbage collection work with your language of choice. Just make sure everybody's in the right place. So just to give you a little bit of background on who we are, both Sanjoy and I are engineers from Azul Systems. We're a JVM manufacturer. Sort of what our claim to fame is we have one of the best collectors in the world that is a fully relocating concurrent collector. I'm not really going to talk about the details of our collector at all today because it's not relevant for this talk. If you're curious about some of the technical details, there's existing publications on this topic. So this is the requisite legal slide I'm required to show you that we're all used to. Now let's dive right into sort of an overview of GC, since I'm sure it's been a while for some of you since you've had your Intro to Compilers course in college. Basic reminder, garbage collector is about managing memory. It's doing automatic memory reclamation in the background for you. There are two basic tasks the collector is trying to solve. The first is simply figuring out which objects are still in use, i.e. which objects are live. That is based on a reachability traversal that starts with a set of known roots from the program. That's going to be your globals, your locals, and any expression temporaries. And then once we've identified what's live, there will be some collection strategy applied. The details of that aren't real relevant for this talk. The important detail to know is that most collectors are going to actually move objects in memory, and we have to ensure that the compiler can go along with that. So we do need some collaboration from the compiler to pull this off. And specifically, we need to be able to solve four distinct problems. First, we simply need to be able to identify the roots for that liveness search in the compiled code. Secondly, if the GC decides to go ahead and move one of those objects, we need to make sure that the compiled code can see that move and not access the old location of that object. Third, we'll need to ensure that the compiled code and the GC can synchronize on a regular basis so that both can make timely progress. And then finally, we'll need to intercept some loads and stores to perform GC-specific actions at the time of the load or at the time of the store. I want to note those sort of last point there is sort of the topic of load and store barriers. We're not really going to talk about that much today. We're going to focus on other topics instead.
So the rest of the talk really revolves around getting a fully relocating garbage collector to use thread stacks as a root set for both marking and relocation. And to be able to do that, the garbage collector needs to look at a thread stack and figure out where all the heap references are in the thread stack. And when it can do so, we say that the thread stack is parseable. The way this is usually done is the compiler generates a site data structure that we call a stack map. And the garbage collector uses this data structure at runtime to really derive the layout of the stack. So how do we make thread stacks parseable? One constraint that we can put on ourselves is we'll always keep thread stacks parseable. We make that an invariant. But that turns out to be too expensive to be practical. What we do instead is that we define well-defined points in a thread's execution, which we call Safepoints, and we constrain ourselves to keep the thread stack parseable only at those points. So when a GC needs to parse a thread stack, it brings the thread to a safe point, parses the stack, does whatever marking relocation, whatever it needs to, and then restarts the thread. So that's how a GC parses a thread stack in this scheme. So this is how a thread stack sort of looks like when a thread is at a safe point. I'm sort of trying to what I'm trying to show here is how a safe point looks like from the perspective of a single stack frame. So you have the youngest frame, buzz, which is waiting for the GC to do something. You have its caller, bar, which is waiting for buzz to return. And you have foo, which is waiting for bar to return, and so on. So what we try to do here is we try to make the youngest frame parseable by the GC at whatever point it is that it's waiting for the GC. And we make older frames parseable at call sites. So if we have the invariant, if we impose the invariant that all frames are parseable at all call sites, practically all call sites, and they're also parseable at the points where it waits for the GC to kick in, the GC can then sort of walk the stack frame by frame and parse it frame by frame. So the way this works operationally, one usual implementation strategy is we get the GC to ask an application thread to come to a safe point by setting a flag somewhere. Application threads periodically check if that flag is set, if there's a pending safe point request. And if there is, it sort of comes to a safe point and then effectively stalls. And application threads need to come to a safe point in a reasonable amount of time, so that dictates how frequently you need to place the polls. And reasonable here can be from a couple of microseconds to a couple of seconds based on your requirements. However, there are some typical places where we'd want to place polls just to have some progress when the GC requests a safe point. So we usually put them in method entries or exits just to catch recursion, and then we put them in packages. And as Philip will mention in the next episode, the right placement of safe point polls can really inhibit optimizers from doing the kind of optimizations you would expect them to do. So just to recap on what we talked about, there are two things that the compiler needs to be aware of. It needs to make frames parseable at the points where it waits for the GC, or safe point polls. That's the green stuff. And then it needs to make call sites parseable, which is the blue stuff here. And this sort of lets the stack be parseable at safe points. And there's also a two-way contract that goes on, that's there between the garbage collector and the code generated by the compiler. The compiler has to assume that any call site or any safe point poll may have the GC just come in and relocate objects. And the constraint on the GC is that it may do so only at safe points.
OK, so we've laid out the problem the compiler needs to solve. But let's assume for a moment we actually know how to solve that. We'll come back to it a little bit later, because we have sort of a proposal we want to make in terms of the representation of a safe point in the IR, where we believe we can improve on it. But for the moment, let's focus on the effect that safe point poll has on the optimizers who are trying to optimize this code. So let's start off with a quick example here. All this loop is doing is it's walking backwards through an array, simply initializing the array with 0. And sort of with the naive C code here, if you run this through LLVM today, this is nicely vectorized and everything works. Unfortunately, that's not going to be the case if we do naive safe point insertion. If we sort of tag these pointers as being GC pointers or pointing to a GC object, and we insert a poll site here, we have some complications that are going to inhibit the optimizer. Specifically, what we're going to end up with is we're going to end up with an opaque operation on the back edge of this loop that is going to semantically introduce new values for p and the array variable that are unknown to the optimizer. At this point, this loop is going to fail to vectorize, and we're going to be running purely at scalar speeds. Now, this is the problem we have to figure out how to resolve. The obvious option here is to go ahead and start teaching the optimizer piece by piece about the semantics of a safe point. This has some unfortunate consequences, and it adds a lot of complexity to the compiler. And because the community of people who are interested in GC is relatively small as compared to the overall LLVM community, it also creates a sort of likelihood of a long tail of optimization work that need to be done piece by piece, and also the more worrisome potential for latent bugs that are only visible to a very small fraction of the LLVM community. From a practical perspective, based on conversations with folks in this room, I believe this isn't really a viable option. Instead, we're going to pursue a different approach, which is going to be to figure out how to run the existing optimization pipelines and then do safe point poll insertion to get the behavior we're looking for. So to put this more pictorially, sort of the early safe point scheme is the top command line there. And the late safe point scheme, which we're going to be talking about, is the bottom one. We're trying to figure out how to accomplish that bottom one, because it seems like it would obviously be better. So to accomplish that task, we need to solve a couple of subproblems. We're going to assume for the purposes of this presentation that we've been handed a set of interesting locations that the garbage collector, via policy, has said, I'd like you to insert safe point polls here. Then we need to go through, we need to be able to distinguish a reference to a GC object from anything that's not a reference. We need to be able to figure out which of those references are live at each particular safe point poll site. Then we need to be able to identify the actual object a particular reference corresponds to. And I'll come back to this point in detail. This is a little bit more complicated than it might first seem. And then finally, we need to transform the IR so it actually has the semantics that I showed in the previous slide. So the first problem we need to solve is distinguishing references in the IR. It's important to note that your typical IR, you're compiling for garbage collected language, will include references to both GC objects and pointers to non-GC managed objects, for example, runtime structures. Then we essentially have two sub-problems to solve here. We need to be able to distinguish between two classes of pointers, and then we need to be able to make sure that the IR isn't manufacturing pointer values for us so that we know we actually have a pointer when we're passing it to the GC. So thankfully, there's actually an existing mechanism in LLVM that gives us almost everything we're looking for here. It gives us everything we're looking for here, and that's address spaces. Address spaces was originally introduced to support heterogeneous computation, but it has the property that there's sort of a disjoint set of pointers that cannot be converted back and forth from one to the other without an explicit cast operation. By simply disallowing sort of that explicit cast operation and the int to pointer cast in our input IR, we get the property we need, which is we're able to distinguish a reference from other values. Now, so the next point we need to make is we need to be certain that the optimizer itself will not introduce such coercions to us if our input IR does not already have it. In practice, we have found that the LLVM IR the LLVM optimizer does not do so. And based on conversations with a number of people in this room, there are actually very good sound reasons where the optimizer will never do so because it actually hurts optimization for it to do so. And then finally, and I'll talk about this more a little bit in a future slide, we've written some verification routines that actually enable us to find such cases if the optimizer ever does decide to introduce a coercion. Now, once we can sort of classify references and non-references, figuring out what's live at a particular poll site is simply going to be a classic liveness analysis, so not particularly interesting for this talk. Nothing unique here. So before I move on, I just want to make a quick aside. So far, sort of talking about this, I've been making the assumption that every reference needs to be tracked and relocated at every central Safepoint poll. This actually isn't the case. There's one classic example is if you have a null pointer, the null pointer doesn't actually point to an object, and its value is almost always going to be invariant for every collector I know of. So you either need to track that for liveness purposes, nor do you actually need to update its value at runtime. There's other examples. For example, if you have a pinned object that is not being relocated, or in many collectors, an object that has been allocated in the current collection cycle, those will not be moving. So you'll need to track them for liveness purposes, but you'll not need to actually relocate them at runtime. So that enables some optimizations. Now, I need to introduce some terminology real fast, just so we're all on the same page, which is the term derived pointers. All I mean by this is a derived pointer is a pointer which is derived from another pointer. So for example, in this case, we've got the pointer q, which is an address of a field inside an object, but it is not a pointer to the base of the object itself. Now, what makes derived pointers sort of challenging is that if you're going to perform a safe point, you need to update the derived pointer to always follow the object it's related to. And if you manage to construct a derived pointer that points outside of that object, so for example, the bit of C code at the bottom here, which is constructing a pointer to the end of an array, holding that pointer over a safe point, and then going back to the beginning of the array to access it. If we have the object P and W in the heap, we have Q that's pointing to the end of P, which is also the beginning of W, and then we move P and W to two different locations, we have to make sure Q follows P and not W. So to do this, we need to identify the base object of every pointer. Doing so at compile time with a little bit of thought I'm sure you realize is a rather hard problem. Thankfully, that's not actually the problem we have to solve. The problem we have to solve is instead being able to find the information at runtime of the compiled code, which base object a particular reference is related to. So as long as we can sort of transform the IR to include that information and record it for later, that'll give us what we need. So we're going to essentially take that example on the previous slide, and we're going to transform it so it looks something like this in pseudocode. We're going to introduce a temporary variable for every pointer we're interested in that is going to track a pointer to the base of that object. And the sort of final result will end up looking sort of like this. But of course, we need to do this for SSA because that's what LLVM actually implements. So we're going to start off with a couple of just basic assumptions here, which are going to be that the return values from a function or loads from the heap are always going to return pointers to the base of an object. This is an assumption based on our source language. It will not necessarily hold for every language in existence. If you have a language that doesn't have this property, we can talk offline about how to generalize this to work for that as well. It's very doable. Then there's a couple of obvious cases that you can sort of apply simple transform rules on the IR to figure out what the base of a particular construct is. If you know the base of, for example, the pointer you're performing a gep off of, you know that the gep itself is also based on that object. But sort of, you can generalize that for a bunch of the IR, but where you have to stop and think is going to be the phi construct, or also the select, but we'll talk about phi really here. So we're going to do exactly the transformation I showed you in sort of that pseudo C, but done in IR. So everywhere we have a phi of that original pointer p, so it's now going to be p1 and p in this case, we're going to introduce a new phi which tracks the notion of the base of that pointer at that location. So in this case, we've introduced the phi p base, which tracks p1 base coming into the loop, and p base, which is flowing around the loop, sort of that is the phi itself. Now, it may be sort of apparent that that phi we actually just inserted is actually redundant in this case. So we can do better than sort of the trivial algorithm I just showed in most cases. This is simply a case of dead phi elimination, but it's a little bit complicated because it has to be interwoven with the rest of the insertion algorithm to actually work. So just to summarize where we are at this point, we have gotten all the information we need to actually insert Safepoints. We have the pole locations, we have the values to be relocated at those locations, and we have the sort of base pointer or base object, or let me rephrase this, the value that will hold the base pointer for each of those objects at runtime. Now, we can go ahead and insert either a Safepoint with gc root, which is the existing mechanism in LLVM, or with Statepoints, which is the mechanism we're going to be talking about a little bit more later. We believe Statepoints is advantageous, but sort of Safepoint insertion here is independent of the representation of that Safepoint. Now, beyond the actual insertion code, we have also implemented that verifier I mentioned. I already mentioned one of the primary uses of that, which is simply ensuring that existing optimization passes respect the semantics required by a Safepoint. But the other sort of two real use cases for this one are if you are going to do early insertion, we recommend you don't, but if you're going to, this is a way to sanity check the IR your sort of front end produces to make sure it's actually using Safepoints correctly. Then it also provides us a way to sanity check the passes we've written that do the late Safepoint insertion. And from a practical perspective, I will say this was incredibly useful in finding all kinds of bugs along the way. Now, the sort of approach I've talked about so far has a couple of restrictions that I mentioned in the slides as I went through, but I just want to summarize so everybody's on the same page. First, we have to have the IR that in its initial form as generated by your language front end has a strong distinction between a reference to an object managed by the GC and any other type of value, including any other pointer type you might have in play. Then we cannot allow derived pointers to escape into the heap because we need to be able, when we load pointers back from the heap, we need to be certain that that is a base pointer rather than a derived pointer. And then finally, as sort of an implementation note, our current Safepoint insertion pass has some limitations with regards to first-class aggregate types in the IR that contain references. There's nothing fundamental about that. We just haven't bothered to actually implement it yet. We will do so at some point, and/or someone else will beat us to it. So back to our example. What have we accomplished at this point? We've taken this sort of simple loop we started off with, And we can now run it through O3, do the full vectorization we want to do, then run it through place Safepoints, and get the Safepoint poll inserted in the back edge of the vectorized loop, not the unvectorized one. To sort of look at the impact of this and sort of show why late insertion is so necessary, consider sort of the simple runtimes I've got up on the screen here. The top one is simply the example I showed you, compiled O0 with no Safepoints at all. So this runs in about 10 seconds. If you take the C example, you compile it with O3, your runtime drops to about 2 seconds. Then if you take that same example, add Safepoints using the early scheme, so before optimization, and then run it through O3, we're still at that 10 seconds. We've gotten no optimization benefit by running this through the optimizer. I just want to note, there's no difference here between the 10-second numbers. That's just noise. So just note. And then the final number on here is doing late insertion and shows that we are able to take this example, fully optimize it, and get the properties we need for the garbage collector with the Safepoint poll on the back edge. Now, just a sort of observation here is everything I've been saying in this section, I've been talking about Safepoint polls, specifically on the back edges of loops or method entries or method exit, depending on how you choose to implement them. All of the points I want to make here about sort of being able to do things late also apply to making the call sites themselves parsable. This is definitely a second order concern, but it does enable additional optimizations in sort of the transformation passes. Because, for example, if you have a read-only method in your language and you do Safepoint insertion up front, you're going to lose the information about that method being read-only because we need that method to be marked read-write to preserve the semantics of the Safepoint. But if you do late insertion, you're able to do any optimization, exploit any aliasing facts that read-only property gives you, and then later come back and sort of put the Safepoints in, and everything works just fine.
OK, so the third episode. So once you have done everything that Philip said, and you're actually ready to insert Safepoints into your IR, and then lower it, generate the code, and do something with it, you need to know how to represent a Safepoint in LLVM IR. And these are our goals of a representation strategy that we want to use. We want the semantics of a Safepoint to follow directly from construction. So for example, we don't want a representation strategy that introduces a new intrinsic or a new instruction that has some weird reordering semantics, let's say, that the optimizers have to learn about. We want the representation to not lock us into a specific lowering strategy. We want to be able to improve our lowering strategy behind the scenes without breaking the interface between late Safepoint insertion or early Safepoint insertion and the rest of the Safepoint logic. And we want to do Safepoint-specific optimizations after Safepoint insertion easily. So LLVM already has a way to represent Safepoints correctly. It's the gc root mechanism. And the way it works is you box every heap reference that could be visible to the garbage collector and hence could be relocated. You box them into alloca slots that you allocate on your stack across calls. So in this case, you have ref, which is in blue, that gets explicitly spilled to box, which is an escaped alloca, so you can't optimize that. And then you have a call to block, which could relocate box in place, the value stored in box in place, and then you load the relocated value from the box once the call is returned. So this is sound, and this is correct. However, we'd like to admit other kinds of lowering strategies. We'd like to, for example, keep heap references in registers across calls. We don't want to always have to spill them. We can do that in GC roots with some interesting lowering magic, but that does not follow naturally because you've already sort of committed to spilling the heap references to your stack, early on in the representation itself. And we'd also like to be able to do some interesting Safepoint-specific optimizations. And for GC root, that means we have to track memory and effectively we want to be able to do simple inst-combine style optimizations where we take a DAG and replace it with some other DAG that it's pretty obvious that they're equivalent. So what we propose instead is a set of intrinsics that we collectively call the state point intrinsics. And it tries to be one level more abstract than GC root in the sense that it does not specify a lowering strategy up front in the representation itself, but it just tries to express the abstract semantics of what a Safepoint poll could do. It's not operational. It does not say that the Safepoint poll spills something and reloads it. It just says that it will do something that is consistent with this interface. And it has an explicit notion of a base pointer. So the notion of the base-derived relationship is expressed directly in IR, and you don't have to follow any convention or run an analysis to figure out the base pointer for a given derived pointer. And the way we sort of try to do this is we represent LLVM heap references as first-class SSA values in LLVM. There is no explicit boxing involved. And our late Safepoint insertion pass and verification passes work on this representation currently. So we propose adding two new intrinsics to LLVM, GC-related intrinsics. The first one is gc.statepoint, which basically is marked read-write, so hence it can basically clobber everything in the heap. And it takes a tuple of heap references and maps them to a tuple of heap references that are individually relocated versions of the tuple that was passed in. So we'll see an example. And then we have this intrinsic called gc.relocate, which is effectively a projection function, which takes the tuple returned by gc.statepoint and then maps out individual relocated values that we use later dynamically. So this is how an inserted statepoint construct looks like. You have gc.statepoint, which wraps a call target and a set of call arguments. So the intuition here is you're really, this is a parseable call side effectively. So you're making a call, and then there's something else that can happen during the call while you're waiting for the call to return. And it also takes a set of heap references that are live over the call. And it returns this token, which really represents a tuple of relocated heap references. But it's an I32, so it doesn't really. What we want to model here is the data dependency. So GC root gets this data dependency by escaping the alloca. So if you have an escaped alloca, then any call can modify it, and hence you have the data. Hence you have a dependence from any read-write call to a load from that alloca. Here we model the data dependence explicitly in the IR, and then you have ref I. I is like for loop, the I you use in for loops, and you have ref I relocated, which the relocated version of the ith reference is mapped out from the tuple or token that is returned by gc.statepoint. And we also have the explicit notion of the base. So gc.relocate also takes a LLVM value that corresponds to the base of ref I. So that it's easy to look up that way. It's present directly in the representation. So we're still in the process of contributing this back to LLVM, upstreaming this. And there's a big patch up for review on the mailing list that adds these two intrinsics to LLVM. And there are lots of interesting work that remains to be done. We can do Safepoint specific optimizations that we do after inserting Safepoints based around either not relocating null or based around derived pointers. There's some infrastructure work to be done, which is interesting, like what can you do once you have inserted Safepoints? And how well can you lower Safepoints to machine code? I mean, ideally, you should be able to lower them such that the entire construct is a no-op. The register allocator puts heap references wherever it wants to, and the GC deals with it. And we can do interesting things with the polling strategy too. We can be a little more, right now we're pretty naive in where we place polls. We can be a little more clever there. So the meta point here is there's interesting work to be done. The easiest way that everyone in this room can help us is we have this big patch which is waiting for review, so please review it. And so, like summarizing everything that we talked about so far, we know how to insert Safepoints late after running effectively an O3, target independent O3. We can do that without significantly without making any significant changes to the compiler itself. The inst combine, for example, doesn't need to know about Safepoints. It just works. And we don't limit any optimization. As Philip's example showed, we get the full effect of vectorization and all other optimizations that LLVM has to offer. So the first link here is a GitHub repository that has the entire layered insertion pass and our representation of gc.statepoints and the whole thing. And we have split off a patch from it, which is just the representation part, and that's currently under review. That's the second patch. So as I said, please, we'd like reviews. So questions?
Let's go ahead and thank the speakers, and then we got Fiverr. So we have 5 or 10 minutes for questions.
Hi, so you mentioned Parseable call sites. So do you transform all of your locatives to the pair of a base pointer and offset for all of the functions that take GC references?
Okay, so I think you might have slightly misunderstood what I was trying to say, or I phrased it badly, I'm not sure which. The short version is that your call site has to be parseable, which means you have to have an indication of what gets relocated at that site, which we represent using the state point. The alloca piece came in with the GC root representation. State points does not use an alloca at all. The alloca, you can think of it as being sort of implicit in that that's a choice of the backend and how it wants to lower a state point, rather than making the stack slot explicit in the IR to start with.
Right, but if you pass a locative or one of your derived pointers to another function, then another function needs to understand if that thing gets relocated at a safe point, that it needs to mess around with the offset that it's using to refer to the object, right?
So, I think I know what you're asking the question of what happens if I pass a derived pointer as an argument to another function, right?
Yes.
Okay. So this was one of the assumptions that I didn't explicitly state on the slide, is our source language doesn't do that. If you're going to do that, you have to provide either an annotation of how to discover the base pointer, or there's a number of other schemes we can talk about offline. It's very doable. It's not done today.
I see. I understand. Thank you.
Hi, can you spend a bit on what's exactly the token and why do you need that on generation, and also why the current position for insertion? Since you can survive all of O3, basically what gets special on cogen? Why do you do the insertion at that point? Can you push it further? Is it advantageous, or why not?
One reason is that we want to do this before certain kinds of transformations are done. Basically, once pointers and integers become the same thing, then you can't do this. So we want to make it as late as possible and still be able to do it.
So in a practical answer, the sort of back-end representation machine instructions doesn't have a distinction between pointers and integers. So unless you want to teach the back-end about that distinction all the way through, you've got to do this transformation at the IR level. We currently do the transformation right before cogen prepare. You could potentially do it even after cogen prepare, but it's not clear you'd get any value. Then you'd also ask a separate question that I lost track of. What was that again?
What exactly are the tokens? So you have one of the intrinsics produce a token, the other one consumes it. What's exactly the semantics on that?
So the token you can think about is simply representing the notion that there's a hash of sort of the relocated values, saying there's a bunch of relocations that got done at the state point. The GC relocate is simply extracting out the relocated value out of that abstract hash. The reason for the token is so that you tie together the GC relocate and the state point into a single series, or the way to say it is the GC relocate gets lowered to nothing. It's a complete abstraction in the IR. All it does is it says it's the value of the relocation of one of the input pointers. Does that make sense?
Yes, but then one issue, we do have quite a few optimizations on the back end. So imagine, for example, what happens, you have that on a loop. We unroll the loop once, and we remove the intrinsics around so that now you get two live tokens, that basically means like 2 live representations of the GC state, right?
Yep.
Yeah.
So to sort of restate what I think you're getting at is late insertion is not perfect. There are going to be some optimizations that run after IR level optimizations that we will not be able to take advantage of without teaching the optimizer further things about it.
Okay,
But
so
we've made substantial progress here, and you get, I'll say, 90-ish% of the benefit. I just made up that number, but something in that territory.
Actually, it's 88. No, sorry.
Yeah.
Any other questions?
With late Safepoint insertion, is it possible to recover types of the objects, or do you rely on the objects carrying their own type information?
So I'll answer that in sort of 2 ways. The first one is separating out source language types at that point is not possible. LLVM IR does not preserve that distinction going through optimization. You'd have to do things, you could play tricks with address spaces to create segments of the source language type system you wanted to preserve, but naturally no. The distinction between a pointer and a non-pointer, and for us, a garbage collected pointer and a non-garbage collected pointer, are preserved all the way through. If you had a subcategory of GC managed pointer that you wanted to accurately describe, you could use another address space to do that. There's no reason this has to be for only a single address space rather than some set of address spaces.
Coming from someone who's somewhat ignorant of garbage collection, is it completely obvious why you get such an optimization performance boost between the different alternatives of inserting save points? Could you break that down just a little more? You've gone from 10 to 2 seconds.
Sure. So the short version there is I'm not showing you anything specific about Safepoint optimizations with that. What that is that's a standard existing optimization that is simply vectorizing that loop. So it's using vector registers on x86 and sort of getting more memory bandwidth, et cetera. The entire point of sort of the late insertion is simply to not inhibit the optimization. If you put the safe point in up front, the existing loop vectorizer is going to see this construct that it doesn't understand, that has the semantics of moving stuff around in memory in hard to explain ways, and it's going to throw up its hands and say, I don't know how to deal with this. That's essentially what we're trying to avoid.
Last question here.
So can you deal with polymorphism? So passing something that may be a pointer or may not be a pointer depending on its provenance.
If you're willing to give me a tag and then teach me about and then teach the Safepoint insertion pass about how to interpret that tag, yes.
Okay,
Otherwise,
cool.
no.
Okay, thank you.
Okay, let's go ahead and thank the speaker again. So we have about 5 minutes between the talks. The next talk will be in here starting at 11:30, and I think it's on the 4th FLT JIT for using LLVM with JavaScript.